Pleasure to be here today to talk about detailing of ABC bridges for simplicity and durability. The idea for this presentation actually came about at a recent meeting where some fabricators were discussing details that are showing up on construction projects that are very difficult to fabricate and difficult to build. And there was definitely a need stressed for simplicity and detailing to make these bridges easier to construct. So that was the basis of where this came from, and what I'm going to present today are some of my thoughts on this subject. There we go. So the key thing is the details presented in this presentation are preferred details that I particularly am fond of. They're not the only details in the world. There's a lot of good details out there, but for the sake of time, I've kind of presented some of the ones that catch my eye. You'll see gold stars popping up in this presentation. Those are the ones that I particularly like, and ones that really solve the problem of being simple and durable. The goal here is to get people thinking about simplicity of detailing. It's something that we should have in our minds when we're designing and detailing ABC bridge projects. And to keep in mind that each agency has different needs, so some of the details presented may not be applicable to your agency, and that's understood. So why should we look at simplified details? One of the big things is risk during construction. These ABC projects tend to be very high-risk projects. They put a lot of pressure on the contractor, and if we as engineers detail bridges with complex details that are hard to fit together, it dramatically increases the risk to the contractor. And one thing that we've learned in the ABC world and contracting world is risk equals cost. High risk equals high cost. And we're always looking to keep costs down on ABC projects. We're also looking for durability, though. We want to make sure these bridges are going to last a long time. So to date, a lot of people, and myself included, have talked about emulation of cast-in-place concrete using precast and steel structures. But strict conversion of this can be a problem, and I'll demonstrate that in a minute. The key thing also is we want to eliminate deck expansion joints as much as possible on structures. We all know that deck expansion joints tend to leak, and these joints, the leakage causes deterioration. Here's an example of a detail. It's just taken off a set of plans from a typical cast-in-place project. It's a bridge that our firm had worked on. It's a two-span curved bridge, and the arrows are pointing at details such as a composite end diaphragm and a cantilever slab over a back wall, and then joint details that are fairly complex. And then if you look on the right, we have a plan view of the same bridge, and you see we throw skew into the equation, in this case almost 40-degree skew. Things get very complicated, especially in the corners of this bridge. If you look at an elevation view of this same bridge, you see that where everything comes together, now we throw grade, a vertical curved grade into this equation. You'll see nothing is really square, level. We have very unusual zigzagging joints, and what this equates to essentially is a jigsaw puzzle. And what we need to do is avoid these type of details where we can, because if we strictly try to recreate this detail in precast, we may have problems fitting it together. So the idea behind detailing for simplicity is to investigate ways to simplify details. However, we do not want to sacrifice durability. So we should avoid complex three-dimensional shapes that are very difficult to fabricate and put together. Avoid sloped surfaces. A level is okay. We typically, many states, many designers detail things like pier caps to follow the cross slope of the road. If it's possible to put the cap in level, it's much easier to fabricate and build. Tolerances are near and dear to my heart. We should account for tolerances in the joints that we lay out in bridges to make sure things fit together. That's probably another subject for another seminar. I won't go into detail here today. There is an NCHRP project on tolerances that is underway at this time. If expansion joints are required, we need to place them where they will not lead to problems. Say for integral abutment bridges, placing the joints behind the abutments so we don't have leakage on bridge seats. That's a good example. And then construction joints, if they are required in sensitive areas, we should look at ways of detailing them to be durable. And I'll show you some details of that today. So I'll start with the top of the bridge and work our way down. We'll start with deck details. Roadway crowns can be a difficult thing to deal with a precast deck. And some states and some details have come out with panels with crowns built into them. And it does add a certain level of complexity to the deck panel design and detailing. It is possible to put a crown on a panel, but when you have a crown, one easier way of dealing with that is to provide a longitudinal closure pour at the crown line. It allows adjustment, both horizontal adjustment of the panels and also cross-slope adjustment during the installation. It's just two less things that the contractor has to worry about when they go to put the bridge together. Deck details, another issue we have is with parapets, and several states have developed these details where the parapet is precast into the deck panel, and which is fine to do. It's something that can be done, but you need to be careful with the detailing. Tolerances can build up, and things will perhaps not fit well together in the field. The contractor in this case is trying to make sure the panels sit properly on top of the beams, and a secondary problem is getting the parapets to line up on the edges. And sometimes those two are in conflict. The result could be what we show in the photo here, where we have stepped joints, which is not desirable, and that could be a problem with regard to the parapet performance. So there's several options we could look at. One is to specify line casting, or essentially match casting of the parapets in the fabrication plant. It is a fairly expensive operation, but it will ensure proper fit-up. Option two would be to place temporary barriers in the shoulder and cast the parapet after the deck is set up and open to traffic. Third option would be to use longitudinal closure pores, as I said before, in the bridge to give you a little more adjustability in the field. And option four would be slip forming, where you do a simple slip form parapet after the deck is installed. Moving on to more deck details, I said before, I don't like expansion joints in bridges, but inevitably you may need an expansion joint on a bridge. And if you have a precast deck panel, the complexity of these details can get quite significant. And the upper right is the detail we showed before. This lower detail is a detail taken from a set of plans on a precast deck project, where we have integral composite end diaphragms. And the idea here is to consider using a closure pore. It'll accommodate the complexities of these joints, especially things like grade and the details needed for the joint system. And also it provides protection for the post-tensioning anchorages if you're using post-tensioning for your deck panels. One way to get a durable deck, durability is part of this presentation, and one way I would strongly recommend is to look at using quality joints in the deck. And these are not expansion joints, these are essentially construction joints. And one way to do that is with longitudinal post-tensioning. This method has proven to be a very durable system for many years. We have examples of these bridges, which I'll show in a minute, of where longitudinal post-tensioning on a bridge can provide a very long-lasting durable structure. So let's get right into it. This is the bridge I'm talking about, the project that I actually worked on many years ago in 1990. It was a replacement of a bridge deck on a curved interstate highway exit ramp. It's a 6-span bridge in Waterbury, Connecticut. A little bit of data on the project. It's a curved structure with straight beams, which made it quite difficult. 6-span bridge with continuous spans, so we had negative moment regions as well as positive moment regions. Single-lane bridge. It was pre-tensioned transversely and post-tensioned longitudinally. It was built in 42 days for the construction of this deck replacement. You'll see some of the photos on the screen. They look a little grainy because they're taken from slides from 1990. They're just old photos. This bridge was built in 1990 and has been in service ever since. And here's what it looks like today. The bridge is in excellent condition. This is a photo of the underside of the deck. The staining you see is not staining from water. It's overspray from a paint job that happened after the deck was replaced. This deck has a membrane waterproofing system on top of it with an asphalt wearing surface. And to date, there are no leaks through these joints at all, including negative moment regions. Another shot of the underside of the deck showing, again, this actually is a negative moment region. So the answer here is we have no leaks, no cracks. In my world, that means there's no problem. So very durable deck. There's virtually no cracking in this deck at all because it's pre-tensioned transversely and post-tensioned longitudinally. So even though we have joints in these structures, if they're detailed properly, we can get a durable structure. This one gets our first gold star for the day. Other ways of getting durable deck joints with non-post-tension decks is to look at reinforced joints. And there's several to choose from. NCRP 1265 developed a detail with I call a bar slot detail, where a steel bar is dropped into a slot and it's grouted in place. These have been tested and proven to be very good for providing a reinforced joint between panels. Other options include small closure pores with hoop bars. We've seen that done around the country. And ultra-high performance concrete is becoming very popular now to provide a reinforced connection between panels. These all work very well. I do caution, though, we need to take care with continuous structures. Negative moment regions can cause quite a bit of tension in the deck. And for instance, the bar slot detail, to my knowledge, was not tested in negative moment regions. And the photo shown there is a bridge showing some leakage of this type of joint. So we need to take care in negative moment regions. So if you have a continuous span structure, what other options do you have? We have a lot of bridges out there that are simple span bridges, multi-span, simple span bridges, and we're redecking these bridges or perhaps replacing superstructures. So another option to look into is this concept of link slabs. And a link slab is essentially a slab that links one span to another that are simple span bridges. The key thing is this is not continuous. This is not a continuous joint. This is a jointless joint detail. It's a lot less complicated than making things continuous for live load. Continuous for live load is a good option too, but again, this is a simpler detail, which is what we're focusing on today. Less expensive. It's great for prefabricated beam elements where we set two elements and connect them together with a simple slab. The reason why I showed this moment diagram on the bottom of the screen is to show that the negative moment region on a typical bridge can be quite large. And if you have even a cast-in-place concrete deck, there's significant deck tension in a typical continuous girder bridge. That we design this by adding reinforcing to the deck to handle the negative moment regions. The idea with link slabs is we don't have continuity, we don't have negative moment regions. We're essentially focusing any potential cracking in the link slab region, and we design the link slab for the rotation of the beam and control the cracking with typical AASHTO provisions. So this gets our second gold star of the day. Here's a little bit on the theory behind link slabs. The idea is pretty straightforward. Essentially, we're trying to accommodate live load rotation of the beam ends and composite dead load rotation of the beam ends. And the way we do that is by debonding a portion of the slab. The recommended portion is 5% of the span length on either side of the joint. And once you calculate your rotations, you apply this equation, calculate the bending moment acting in the slab, and then you design the slab accordingly. And we recommend you design it for serviceability as well as strength. Key thing I always bring out here is the term I, this EI over 2EI theta over L. The tendency of most engineers when they're worried about durability is to go ahead and make this joint thicker, make it a thickened slab at that location to get more strength to it. But in link slab design, the rotation is given. That's your live load rotation. If you say, for instance, double the thickness of the slab, moment of inertia of the slab is 1/12 BH cubed. So if I double the thickness of the slab, I increase the bending moment acting on the slab by a factor of 8. So we do not want to do that. In anything in link slabs, we want to keep this link slab thin. We typically say keep it the same thickness as the slab on either side of the joint. So a little bit of theory on link slabs. Why do we like this and why do we give this joint a gold star? This is an example of the link slab bridge north of Boston on Interstate 93, a project called the Fast 14, which many of you may know about. This is a bridge. While you don't see any vehicles in the photo, this bridge carries approximately 190,000 vehicles per day. And this is a shot of the bridge after it was open to traffic. And there is no leakage of these link slabs. They're performing very well. So a good testament to these details. Moving on to pier caps. Pier caps are common in a lot of states. Different types of pier caps exist, but open frame bents are pretty common. And this is what I mentioned before about detailing pier caps to be level, not sloped. While it is possible to slope a precast pier cap, it just adds a level of complexity to the detailing and construction. So if you can live with a flat pier cap, we recommend you do that to simplify the connections. The photo on the upper right is a photo of a bridge in Massachusetts where this was done. In this case, the pier cap was built and detailed as dead level. And the variation in cross slope was handled by the dimensions of the top of the cap. You could also add beam seats to accommodate the vertical variation from beam to beam caused by cross slope. Another idea, if you have skewed ends, sometimes we show skewed ends on pier caps for architectural features. If you don't need to do that, if you could square the ends off, again, it's just easier fabrication and less cost. Another detail that's been researched that's a very good detail, it's shown in the lower photo, it came out of a research project NCHRP 1274. It's a seismic connection. Tested, it performs very well, but what I recommend here is whatever connection you choose for a pier cap to column connection, engineers should really take a look at the congestion or reinforcement in these pier caps. It can get quite congested, as you see in the upper photo. So whatever connection is chosen, the engineer should look into this to make sure that it's actually can be fabricated. I've heard many stories from fabricators of details that come out that cannot be built because the engineer drew the reinforcing bars as dots on a plan and not realizing the actual diameter of the bars and the spacing of the bars, or perhaps even lap splices in the bars. So something we should keep in mind when we detail joints. The grouted post-tensioning ducts shown in the lower photo are a very good connection. We just need to make sure we can fit it and the fabricator can build it. Integral pier caps are very popular in high seismic zones out west, and they're fine details, but they're virtually impossible to purely emulate with precast. There's just too many elements coming together, too many tolerances to account for, and too many things to connect up. So the result is typically a semi-precast connection, precast cap, and this photo here is taken from work done in precast concrete, where we set a precast cap on a column and then set the beams and then do a large closure pour. While this is all fine and it's been tested and they work well, the closure pour is fairly complex to detail, fairly complex to form in the field, and then we need to wait for that closure pour to gain strength. So what I recommend is you consider, even in a high seismic zone, if you can make it work, to go to a more conventional East Coast design where you do not have an integral bent cap. You essentially have details similar to what we showed before, with a bent cap with the beam sitting on top with a bearing. It just results in faster construction and less chance for fit-up problems. Column detailing is another one of a way that we can save on fabrication costs and simplicity. We all like building round columns. Round columns are very desirable, especially in high seismic zones. But round columns are difficult to fabricate. If you think about it, I need a hole to pour my concrete into a form in a fabrication plant. In a round column, the only opportunity we have is at the ends. So the fabricators need to cast these columns vertically, which is more difficult than casting things horizontally. If we go to a faceted column, in this case an 8-sided column, the blue box represents a potential form for this element. And what we do is we leave one facet unformed, or we can pour the concrete in the side, or in this case laying down flat would be on the top, and then it's much easier to fabricate, and it opens up the opportunity to build a form that's, say, 100 feet long and cast 4 or 5 columns at the same time. So this greatly can facilitate construction, fabrication, I should say, in the plant, thereby reducing costs and saving money on the entire project as a whole. You still get the benefits of a round column by using spiral reinforcing. So it's just a recommendation if you can, if you're not particularly picky about the shape being faceted versus round. It's a detail that we do recommend. And for that reason, it gets the gold star. Base joints, we've heard in many presentations in the past, we've heard concerns about durability of these base joints on top of footings. The reality is it hasn't been the case. We have not seen durability issues with these joints. But if it is a concern, one detail that was developed by the PCI Northeast Bridge Tech Committee is to recess the detail several inches into the footing and then pouring a secondary grout pour, essentially a belt suspenders approach, to add additional protection around this detail. It adds a little thickness to the footing, but it can provide more durability and essentially double protection for the joint. The key thing is if this joint did deteriorate in the future, it would be easy to just go and repoint the grout if the grout deteriorated, and that's been a concern with many agencies. And it really is something that can be fairly easily maintained in the future. Now moving on to some more unique details that we see around the country, and this is one that I really like a lot. It was developed by the Washington State DOT. This falls in the category we like to call stupid simple details. It's so simple and easy that it's something that we should definitely consider. The idea here is to essentially build a bridge pier or the wall upside down. Normally we cast the footing first and then cast the wall panel second. In this case, we're going to cast and set the panel first and then pour the footing around the panel or column. Very simple, easy connection. It's a standard, essentially emulating a cast-in-place connection precisely. So it's something that's very easy to pull off. There's a temporary strut is typically used that's cast into the column or wall panel to set it temporarily. It's braced off. Set your reinforcing and pour your footing. Still very fast construction. This detail probably adds maybe 1 day to a construction schedule compared to, say, a precast footing. So it's something worth considering. So for this reason, this one gets a gold star as well. Now we get even a little more radical. This is a detail developed by Washington State DOT using a research grant from the Federal Highways for Life program. This is a concept where the precast column is set similarly on the ground ahead of time, and then a footing is cast around it. But the interesting thing on this detail is there is no reinforcing passing between the column and the footing. You essentially are doweling this footing into the cast-in-place footing. You set it on a leveling pad with the reinforcing. In actuality, without having bars coming out of the column, you could actually set this after the reinforcing is fully placed, and you simply pour the footing around the column. This has been tested for seismic loading. We can develop the full plastic moment capacity of the column as long as the footing is adequate depth. And it's very simple, easy to build, very durable, and still, like the last detail, fast construction. So this one also gets a gold star. A little bit about column durability. There have been concerns expressed with grouted sleeves or grouted post-tensioning ducts, which are very good connections for strength. This is a great example. This is a bridge in Fort Myers, Florida, built over 20 years ago now. It's a bridge built over brackish water, so we have salt in the area. It's a very corrosive environment, and yet this bridge is still in very good condition. So this bridge was built with grouted couplers. Grouted post-tensioning ducts should have similar durability. So the concerns that people have over joints really are not necessarily founded. The key thing, as I said before, long-term maintenance for these joints would simply, if the grout did break down for whatever reason, you could simply repoint the grout, removing portions of the grout, and repairing the grout in the future, similar to what you would do in a masonry structure. So really, these joints, for lack of a better description, are no different than a typical construction joint in a bridge. This falls under the category of another detail that I call stupid simple. It's very easy to build and very effective. A detail developed by Iowa DOT for connecting integral abutments to piles. A similar detail was used on a seismic connection under NCHRP 1274, another great detail. In this case here, we're looking to connect the pile to an integral abutment panel stem. Now, we love integral abutments because they're very durable, because there are no joints to leak and cause deterioration of beam ends. So they're excellent bridge types, but we need to figure out how to pull them off in an accelerated manner, and these are the details we like to see. They're very good for seismic, and we like these simple details where essentially we cast a stem with a corrugated metal pipe, simple drainage pipe, cast into the stem ahead of time. These drainage pipes can serve two purposes. One, they can connect the pile to the stem, and two, they can reduce some of the weight of the piece. The photo shown in the upper right is a bridge being built in Massachusetts. This particular bridge had 2 piles per precast stem. You'll notice there are 3 voids in the stem. The third void was simply added to reduce the weight of the shipping weight of the piece and make it easier to erect with smaller cranes. The CMP voids essentially go around the pile, filled with concrete, and you're good to go. These have been tested for very significant vertical loads. They can handle, essentially you treat this thing as if it was a punching shear calculation in your calcs. And the detailing of the actual integral pier cap can be standard detailing as if it was cast in place. It's a very good, simple detail, very fast construction. Typical construction for one of these integral abutments is less than a day. So for that reason, this gets another gold star. More graphics of that same detail showing how the corrugated metal pipe voids are cast into the pieces. And one thing I'd like you to take away from these graphics is to look at the joints between the pieces. They're just shown as a simple grouted shear key. Also showing a back wall on these things. If you can accommodate the weight to have a back wall cast in the shop such that once you set these pieces, you just set the beams, form the front portion of the diaphragm, and you're moving forward quickly. Just an example of little things you can do to speed up construction in the field without making the complexity of the detailing too difficult. So let's talk a little bit about these joints. There have been some states that have been using transverse post-tensioning to connect these members together. This combined with match casting, and there's nothing wrong with that. Match casting is very common in our industry. It provides a very good, durable joint. However, it does probably add a day or two to the construction for these abutments. A concept has been developed, used in several states, Utah and Massachusetts, where we just use a simple shear key connecting the multiple panel pieces together. The question is, how do we accommodate this in design? And we're going into a little bit of education here. We're drawing a free body diagram. And we look at a free body diagram. The first one on the top is your cast-in-place construction free body diagram, where essentially it's a multi-span continuous structure, and we design it as such. This is showing vertical loads. A similar diagram would occur for the horizontal loads. By putting the shear keys between panels, we essentially put a pin joint between the panels. We still have a free body diagram that is stable, and we can design it. So the engineer can now design and detail the reinforcing, just assuming there are pins at those shear keys. Once you get past that, it's simple, just reinforced concrete design, and you can make it work. These have been built, and they perform very well. Moving on to a different abutment type now, we're looking at semi-integral abutments. And the semi-integral abutment is essentially defined as an abutment without, where a portion of the abutment is connected to the superstructure. However, a moment connection is not required at the interface between the superstructure and substructure. The idea here is to set the piece on the abutment with a pin joint, typically a bearing, and then to have the integral abutment overlap the back of the abutment as shown in this detail. This detail shown is actually not an ABC detail. This is a detail from the Washington State DOT Bridge Manual. This has been done for years in Washington State on cast-in-place construction, and the idea here is to migrate this type of detail into precast construction or prefabricated construction. The photo shown below is a bridge, an SPMT bridge. I believe it's in Utah, where this detail was taken and included into the SPMT bridge move. And essentially, when the bridge is moved into place, it's set over the abutment with that overlap. The overlap is critical to ensure that water does not leak through the joint, because the water has to flow uphill to get over the joint. Very simple detail. It's great for prefabricated beam units. It's very good for SPMT bridge moves, and it's also very good for lateral slide projects as well. So very cost-effective, durable detail, and it's great for these technologies that I list here. This gets a gold star. Another concept of integral back walls, semi-integral back walls, is if you're going to use a cast-in-place deck or, say, a precast panel deck, is this detail was developed in Utah, and I used, again, this is a bridge in Rhode Island, where essentially we precast the back wall and bolt the back wall to the back end of the girders as we set them. And it could be done with precast concrete or steel girders. Simple joints are detailed in the back wall, similar to what we showed before with the integral abutments. And then the deck is poured. When the deck is placed, the deck is connected to this back wall to form the semi-integral bridge. This detail is very cost-effective, easy to pull off in the field, results in a rapid construction technique. And one other added benefit is the precast back wall can act as your end diaphragm, so you can eliminate the end diaphragms between beams using this detail. For that reason, this gets a gold star as well. Cantilever abutments are still used in different parts of the country. Sometimes we have cantilever abutments on piles. Other places have it on shallow foundations, such as spread footings. One detail that was developed recently, this is a bridge in Massachusetts, and it's been used in other bridges around, to take the same concept of the corrugated metal pipe voids for integral abutments and applying them to these cantilever abutments by projecting reinforcing out of the footings and into the corrugated pipe void and filling it with concrete. These are great for low moment demand connections, so stub abutments or relatively short abutments. This works really well, and it's very simple, very fast, and very cost effective. We don't need to use a lot of mechanical couplers. It makes things a little easier to put together, and the tolerances are much more forgiving. Again, this gets a gold star for that reason. The idea behind this is to, another thing we can do with this type of detail is to use the concept of a cap piece placed over the wall stem panels. And the graphic on the left shows this concept. The idea here is to use the corrugated metal pipe voids in the wall panel and then use a doweled reinforced connection between the wall panel and a separately made cast top piece. The idea here is to have simple details for these heavy wall panels and just have one or two complex details for the cap. So the fabricator may have to spend a little bit of time casting this cap piece, but the majority of the precast on this abutment is very simple detailing, simple rectangular pieces with voids. And again, this is the joint located at the top near the bridge seat is a very low moment demand connection. Very easy to get this work with a simple dowel connection. For this reason, it gets a gold star. The detail shown on the right, let me back up. The detail shown on the right is showing essentially a cast-in-place abutment that was converted to precast abutments using the details I've been talking about today. Maine DOT recently built a bridge, and I'll thank Maine DOT for these photos. They sent them to me the other day. This is a great example of how using wall panels with corrugated metal pipe voids attached to a footing. In this case, they had a cast-in-place footing. And then once the wall panels were set and grouted, a simple cap piece was set in place. And I think we could all agree this is a very attractive-looking abutment, very fast construction, very durable, and very simple to build too. So this gets it hits on all the cylinders that we're looking for something that's durable, fast, and easy to build. So we'll give a gold star to Maine DOT for this one as well. Approach slabs, moving on, have been problematic. Some states have had difficulty setting grade on approach slabs. So one concept that we have, instead of using a sleeper slab, if it's possible with the detailing you have in your state, is to look at using flowable fill or non-shrink grout at the ends of approach slabs to seat these things properly. We've seen contractors labor over getting the approach grade set just perfect so the slab will sit nice and even on the approach soil. This is a way of having fairly rough approach soil and using flowable fill to seat that approach slab at the end. It's faster and less expensive than other details that are out there. If time is critical, you can use non-shrink grout, but flowable fill is a great material. It doesn't have a lot of strength, but we don't need a lot of strength in this connection because essentially the seating of the slab has to be essentially as strong as the soil underneath it, which is not very. So it's something we can do very inexpensively and quickly and save some time in getting these things set to grade. Another option that's been used in Massachusetts is to take the approach slabs and set them below grade. In this case here, the approach slab is set about 12 to 18 inches below the final pavement elevation. The detail developed by Mass DOT. It allows you to set the approach slabs with much wider tolerances. They don't have to be set perfectly to grade because the pavement placed on top later will accommodate the final grade. So it's a nice little detail used in Massachusetts. It's actually been used for years in Massachusetts. It can be problematic with utilities, so you need to look at that a little bit, but it's something you may want to consider. Other details, Utah and other states I know do this, where they have attached the integral approach slab parapet is attached to the end approach slab. So it'll save some time in construction and provides a nice little detail to simply get that parapet in place or that barrier in place built on top of the approach slab. If you happen to be building soldier pile walls, precast concrete's an option, and now we're jumping back into these corrugated pipe voids again, where by putting a corrugated pipe void within a wall panel, in this case, the panel looks like a double T turned on its side. The idea here is to reduce the weight of the piece by having it shaped like this, but the corrugated pipe voids provide an excellent connection to the piles or drilled shafts. If they get tall, you can add soil and rock anchors to make it work. Again, fast, easy, and durable. Prefabricated deck beams are becoming very popular, and that's because the work required to connect, say, a precast deck to a girder is fairly complicated. We talked about post-tensioning before. So the concept of casting the deck on top of the girders ahead of time and then placing these things span by span, connecting them with link slabs, and then connecting them longitudinally with closure pours have become quite popular. This is a photo from the Fast 14 project showing the precast deck on 2 steel I-beams. You could also do this with a single box beam. You could also look into the folded plate beam that is being used around the country as well for shorter spans. So the concept here is to have it precast ahead of time in beam units, decked beam units that are connected in the field. Construction is very fast. These things, the Fast 14 bridges were built in 48 hours, so it's something that can be done in a weekend. If you have more time, it's definitely still something that's very viable. This gets gold star as well. Some photos of the Fast 14 construction. I actually showed this bridge before with the link slabs. This bridge, again, 190,000 cars a day, and it's performing very well. Precast is not left out of this deck beam element world. PCI Northeast has developed a heavy-duty double T called the Next beam. There are 2 versions of this beam that are currently in the market. One is called the Next F, which is a form where a reinforced concrete deck is cast on top of the beam after the beams are set. The beams act as forming and do not need to be set or stripped. There's also a D version, which is a deck section that is connected with small closure pours between the units. I say here it's very cost effective. These beams are coming in very inexpensive, relatively fast construction. We're looking at about 5 to 7 days to build a superstructure, maybe even a little less. And again, there's very limited deck forming and stripping, essentially limited to just the ends and the edges. No cross frames in these bridges as well, so there's less pieces to handle. Details are available at pcine.org. One thing you need to be careful about with precast deck sections is to accommodate vertical curves, and the PCI details that are available at pcine.org include, very shortly, these are about to be posted, we'll include details on how to handle things like camber and vertical curves. And the key thing to keep in mind is sometimes the top flange of these deck sections might change thickness. Now, if you have a steel section with a cambered girder, you can accommodate this with the girder camber. But for precast sections where the beam is going to come out of the form with a given camber, you may need to adjust the top flange thickness to get your vertical curve to work. So in conclusion, it is possible to emulate cast-in-place concrete, cast-in-place construction with prefabricated elements. But just because we can emulate cast-in-place concrete doesn't mean we should always do that, because it can result in some very difficult details that are difficult to fabricate, construct, and increase project costs. So knowing those problems that could exist, and I gave you one or two examples today, minor changes in bridge detailing can really solve your problems. The key thing is to look at improving fit-up and constructability, and that leads to saving time. By doing that, we also reduce risks to the contractor, which reduce costs, because as I said before, less risk equals less cost. And the goal, again, is to improve durability. And hopefully, the details I've given the gold stars to today and other details that are out there will provide very durable structures. Hopefully, we've demonstrated to you that it is possible to get durability and also have simplicity of design and detailing. So it's possible to get everything that we want: easy construction, lower cost, faster construction, and improved durability. So with that, that concludes my presentation. I'll be happy to take questions.
All right. Thank you, Mike, for a great presentation. Very interesting. So at this point, Ben Bierman is going to be moderating the question and answer. We received a number of questions on the question box. Ben?
Okay, thanks, Adirad. And Mike, great job, just as Adirad had said. And you, sir, get the gold star for doing such a great job.
Oh, thank you so much, Ben.
So we've got a series of questions here.
Does that mean I'm fast and durable?
Actually, we're going to give you double gold star. How about that?
Okay.
Yeah, fast and durable. All right, let's get on with the getting here. Mike, you demonstrated a lot of great details here, but can you go kind of high level and perhaps maybe talk to the group and what are the best practices just for closure pours, rules of thumb, things that, look, when you get into this, what do you got to have in mind? And this is common with everything.
Great question. And the key thing is that materials really play into closure pour. There's different details out there. There are details with straight lap bars that are usually about 2.5 to 3 feet wide. We have details with hooked bars that are in the order of 12 to 18 inches wide. And now we have UHPC joints that are down in the order of 9 inches wide. The key thing, in the Fast 14 job had fairly wide closure pours. The reason for those closure pours being so wide hinged on a number of factors, and primarily it was shipping width of the units and the shipping weight and handling weight of the units. But making the joint wider, it reduced the weight of the precast pieces. And that was that particular project. That was what drove that project. You can go with narrower joints, and like I said before, with hook bars in concrete or straight bars in UHPC and very narrow joints in the order of 6 to 9 inches. The key thing is the material that goes in the joint. We have to be careful not to just put standard concrete in these joints. That the reason for that is we are casting the concrete against precast concrete with dowel bars, and essentially it's a confined condition. So when that concrete goes to shrink, it will crack. So what we recommend people do is looking to develop mixes that have admixtures to control shrinkage in the concrete going in the closure pour. It was done successfully on the Fast 14. It will increase the cost of that material because admixtures have to be thrown in there to control cracking. There have been several studies done, one by Washington State DOT on control of cracking in bridge decks, where they found that these admixtures could reduce shrinkage approximately 50%. So I really am a strong believer in putting quality material in these joints, and controlling shrinkage is one of the most important things.
Absolutely. Don't forget the Ultra High Performance Concrete Initiative that's coming down for the EDC3 round. And also, you know, those things that we've said before, keep it simple, keep it clean. You know, there's a fabricator that has to put this all together. Keep the joints clean. Make sure the joints aren't working, right?
Actually, you bring up a good point. I meant to say this. One other thing that's been found, especially with the UHPC work, is the edges, the shear keys on the edge of these panels, either the deck panels or the prefabricated beam units. It's very important to not use just a formed surface there. It's very important to use exposed aggregate surfaces on those shear keys. That is found to make a dramatic improvement in the performance of these joints by having the closure pour concrete or grout or UHBC bond much better to the adjacent precast element.
Yep. That and a little bit of water, right?
Yeah, yes, you should pre-wet the building.
Okay, pre-wet it so it's not pulling out the water and whatever material that you're putting in there. Okay, let's move on to another topic here. Let's see here. This is funny, kind of cute. On your first Gold Star bridge, which was the deck panel flyover ramp, using the deck panels, do you know what the ADT was on that bridge?
Offhand, I do not, but I do know there's another bridge that was built about 20 miles south of that bridge in the town of Seymour, Connecticut, which is actually my hometown, with the exact same details. Bridge is also in good shape. It was built 2 years after this bridge was built. That bridge has an ADT, I'm going to guess about 100,000, 75 to 100,000 cars a day. So while the ADT on this ramp was relatively low, the ADT on the second bridge built in Connecticut was quite a bit higher.
Okay. Here we go. What transverse joint stress do you recommend for the longitudinal PT decks?
Transverse joint stress. Well, the AASHTO LRFD specifications have a provisions in chapter, I believe, chapter 9 for precast concrete decks. In that provision, they recommend a pre-stress, a net pre-stress force of 250 psi across the post-tension joint. My understanding is that provision came from other research on transversely post-tension double Ts in Florida. However, over the test of time, that 250 psi seems to work very well. It was a good recommendation. So if you designed at 250 psi, or possibly even a little bit lower, Virginia Tech University had done some research and found that perhaps that number could be lowered to maybe 200 psi. So we found that if you detail for that stress range for final net post-tensioning, you will have a very durable joint. And that has proven to be the case around the country.
Excellent. Now, you travel all over the place. Do you see or do you run into issues with obtaining contractors who are qualified to do the post-tensioning?
It hasn't been a major issue, Ben. What I like to call post-tensioning of a deck panel is like post-tensioning 101. It's about the simplest post-tension you're going to do. It's not like post-tensioning, say, a segmental box girder. We found states with very detailed specifications that work really well. We've also seen states with fairly loose specifications, and the contractors are wise enough to bring in subcontractors to help them perform the work. So we've seen good results either way. I'm a firm believer in having a good set of specifications put together, requiring pre-qualified post-tensioning contractors. And then the key thing is to make sure the grout is placed properly in the ducts. The tensioning is fairly straightforward, but the grouting is usually where the problems occur. So there are some very good guides out there. Federal Highway, I'll give them some pump here. Federal Highway's got an excellent manual on post-tensioning that is available online. Also, the Post-Tensioning Institute, PTI, and ASB also have very good documents that engineers can use and owners can use to help develop specifications that are very pretty much ironclad specifications.
In PTI, I know FHWA folks are looking to do some PT, and they just need to get refamiliarized with that. Just reach out to us, and we can bring people out there and get your contractors up to speed. Mike, this question came up around slide 29. I don't know if you want to pop up a visual there. It had to deal with the abutments with the corrugated metal pipe. The question was asked, is there any re-steel or reinforcement steel that passes through the corrugated metal pipes?
Great question. The answer is no. The research done for cap-to-column connections under NCHRP 1274, that was a seismic detailing research project where we're connecting a column to a cap. That research did have bars passing through the corrugated pipe void, which is understandable in a seismic connection where we're trying to develop plastic hinging. But for this particular connection, the answer is no. Also, in the past, we've seen detailing where people will, say, shoot shear connectors on the pile to get the pile to grab onto the concrete better. But the reality is you don't have to do that either, because the pile, if it was cast-in-place construction, the pile would be embedded in a cast-in-place wall stem without shear connectors. So it's really not necessary. Really, it's just a simple, that's why I call it a stupid simple detail. You set the piece over the pile and you fill it with concrete, and you detail it essentially the same as if it was cast-in-place construction. So it's a great simple detail. It was tested at Iowa State University. It's very durable, very strong. The testing at Iowa State, they almost couldn't fail the connection. That's how good it was. So that's why we like it, and that's why it got the gold star.
There's the gold star. And here's a related question to that. How is the joint between the abutment and the U-shaped wing wall detail? And I think it's specific to that.
Probably this one here too. Yeah. We've seen it done several different ways. This particular detail is calling for grouted splice couplers. It is possible to couple two pieces of precast together in a horizontal plane with horizontal couplers. We've also seen it done where a small closure pour, you have the precast wing wall is just set with lapped bars and a closure pour between the two. The reality is, on an integral abutment, you're going to have a closure pour for the end diaphragm and the abutment. So having a small closure pour between the wing wall and the abutment stem is not going to slow construction down much because you already have to pour and cure the concrete for the end diaphragm. So if you have to do a closure pour, that's a very simple, easy detail to pull off, and it really won't slow down the overall construction much at all, if any. Grouted couplers can also be done as well.
Here's a question on the neck. Oh, go ahead.
No, I was going to say you can use soldier pile walls too, but the integral flying wing walls are pretty popular with integral abutments.
Okay. There's a question on next beams. Have you seen utility hangers cast into the open area between the legs of the next beams?
Great question. The answer is yes, and that's one of the reasons the next beam was developed. In the Northeast, we have been building a lot of adjacent box beam structures, and utilities were always problematic. We'd hide them under sidewalks, hang them off of parapets. It was more of a problem. The idea behind the next beam is, yes, that's the goal, is to hang utilities underneath these beams. PCI Northeast at PCINE.org has details that are developed for, we usually recommend putting inserts on the underside of the slab as opposed to inserts in the side of the stem. Side inserts are more difficult to fabricate. You actually have to drill a hole in the side of the form to hold that insert in place. Putting an insert on the underside of the top flange is actually a simple operation where they essentially glue the insert down to the form. And then when they pull it off, when they strip the form, it comes off with the piece. So there are details available at PCINE.org.
Okay. Staying on the next beams, there was another question between the next beam Ds and the next beam Fs. Mm-hmm. One state DOT is experiencing cracking. I guess it looks like here the cracking of the joints between the beams for the next beam D version, and so they're kind of switching gears and they're moving over to the F version and pouring the deck. And the question was, do you know of any other issues from perhaps other states that are experiencing, I guess, cracking with the next beam Ds?
Ds, no. We have some issues with F beams, with skewed F beams. There's a crack that will develop on the inside. If you can see my pointer, hopefully you can. On the inside of the stem of the obtuse corner at the ends of the beam, we're seeing cracking there. The committee that developed this beam, we knew that crack would occur because it occurs in double T's for parking garages as well. We included a significant amount of reinforcing in the end of the beam to control the width of that cracking. However, the cracks do occur with skewed F beams. We occasionally see them with square F beams. The committee didn't think it was a significant crack because, again, the top flange is simply a form to hold up the concrete for the deck pour. So it's just a simple repair is to essentially seal that crack to prevent moisture from getting into it. We have not heard much of cracking in D beams. There's quite a bit of reinforcing in these beams because the top flange of the beam is the deck of the bridge. I thought I may have heard you said there might have been cracking in the joint, and that kind of goes back to the material you place in the joint. A lot of engineers are specifying non-shrink grouts, and Ben Graybeal from Federal Highway will be the first to tell you non-shrink grouts sometimes shrink, and sometimes they shrink quite a bit. So if you have a grout that shrinks quite a bit, you will get cracking in that joint between the two beams, and it could be a problem. If you do get cracking, the cracks can be sealed with things like methacrylates, but really, again, it comes down to the material you place in that joint. And UHPC is something that we're strongly looking at in the Northeast to use for that joint as well.
Okay. Let's hop on over to the link slabs.
Yeah.
There's a question. Do you have a do you need to have a fixed bearing to use the link slab, or can it be sort of a fixed expansion? That's around slide 17 is where your link slabs are at.
That's a great question. Actually, the answer is you want to have one of those bearings be an expansion bearing. The idea was if you have a fixed bearing, the moment applied, the rotation will develop a couple moment between the slab and the bearing. And that actually will cause problems, probably start bending anchor bolts over and things like that, and perhaps causing more cracking in the deck. It's important that you have at least one expansion bearing down below to allow this joint to rotate relatively freely without generating a large moment. So that's a very good point to bring up, that you need to have, ideally, two elastomeric bearings work great. Having one expansion bearing is probably all you really do. So I'd recommend that as well. The detail also brings up a good point, that if you have two different beam depths, link slabs work well for that situation as well. And in many cases, end spans of multi-span bridges have variable beam depth. So it's a good solution for a lot of reasons.
Okay. I'm sorry, Mike. I was reading this question that came in here. I'm just going to read it word for word.
Go ahead.
How can you minimize transverse connections between deck panels? Usually with cast-in-place transverse joints, they're always a concern, and the goal is to minimize the joints. How can we justify more joints when using precast deck panels? Okay.
Well, the width of the joint, I mean, the number of joints you have in a structure is a function of the size of the panel. If you can make a panel wider and you can ship it to the site, then you can go, say, for instance, if the state has shipping limitations of, say, 14 feet, you can try to make the panels 14 feet wide as opposed to, say, 8 feet, which is a pretty common dimension. That's one way to minimize the number of joints. There's other details that are being developed where we run the panels lengthwise instead of transversely. And using UHPC, we can make connections of the panel to the beams with a longitudinal pour over the beam flanges using a very narrow joint over the flange. In those situations, we're actually using the flange as the form for the closure pour. So there's some really interesting details being developed, especially in the UHPC arena. I just suggest people keep their eyes open for these details, and maybe, Ben, you could add some more about the UHPC work you're doing with Federal Highway with regard to these types of connections.
Well, that's a whole topic that we're ready to unleash here. I don't think we'll have time to do it with the Q&A, but because I want to stay focused on what we got here, because there's some really good questions here. Let me give you another one. This is really good. Is there, and folks, the UHPC stuff, we're getting prepared to kind of really roll that out in the next month or two here. You'll start seeing a lot of good information. But let's get back here. I like this one. Is there hard data on the durability of cast-in-place versus prefabricated elements? How does prefabricated relate to service life design approaches? For example, like the 100-year bridge design. Beneficial or indirect, particularly as it relates to the detailing issues presented?
Good question. The answer, hard data, the answer is probably no. I would imagine, I know Federal Highway has a long-term bridge performance program underway, and I am not sure, maybe Ben, you know better than I do, whether or not that program is going to look at precast versus cast-in-place decks. You know, unfortunately, we don't have thousands of these bridges out there. We probably have hundreds out there, and that perhaps that long-term bridge performance study will investigate this. But to my knowledge, the best data that we have is the several bridges that we have that are over 20 years old that have been in service that are performing well. Another thing we do, Utah DOT has built 15 or 20 of these bridges with precast decks. And what Utah DOT does is every year or two they go out and inspect these decks, primarily looking at the performance of the joints, performance of the system. And our firm has been involved in those inspections, and the long and short of it is the post-tension decks are performing very well. Some of the decks that have welded tab connections and maybe some of the details that I didn't show today are performing not so well. We have some leakage issues. So we're finding that's why the post-tension joint got a gold star, because we've seen very good performance of those structures. However, some of these other details with UHPC and reinforced concreted joints, they work very well as well.
Yeah, and I'd like to add to that, Mike, because we really see the evidence. You know, Mike Keever with Caltrans, when we were up at TRB, he made mention to this, and I'm familiar with the project. in which they had deck panels out there in the Bay Area, and they were doing a redecking because they needed more deck area for expansion purposes, not so much for durability and degradation issues. These deck panels have been in service since the 60s. They don't even have an overlay on them. And it was like one of these, wow, I think we have the oldest deck panels here in the U.S., and when they tore them up, they were fine. It was amazing. So, and I think owners are seeing that. You say, well, look at your deck panels that are built at a certain time frame, and look at your other cast-in-place decks. And I'll talk about decks because it seems to be the most controversial. And compare the two, and tell us. You tell us which ones do you feel are performing better, same, or worse. And a lot of times you hear people saying it's either better or the same. You don't really hear a lot of this is worse.
Right. There's other good examples too, Ben. Is the Woodrow Wilson Bridge in Washington, D.C. was built. There's a nice new bridge there now. It's a very famous bridge. But prior to that, about 25 years ago, that deck was replaced with a non-composite post-tension precast deck. And there was a study done by, I believe, Virginia DOT looking at the durability of that deck. And there were some issues. They had some through-bolted barriers they put down that where the water was getting through the bolts and causing deterioration. But by and large, the post-tension joints were doing very well. So there has been some lessons learned there. The bridge in California you're mentioning, the first project we did in Connecticut, the one I showed in Waterbury, Connecticut, we actually used some of the details from that California bridge that you were mentioning as the basis of some of the details we used there. So it's a good testament to good details that work well over time. And those details are still being used today on projects almost daily. So there are some very good details out there. Things like the shear connector pockets with grout that perform very well.
I need to check in with Adirond. How are we doing on time, Adirond? I can go longer? It's your call.
We probably have time just for one more question, Ben.
Okay. See if we can get a good one here. Well, we were talking about, let's get off of that. Okay. What is your experience with precast units for piers adjacent to railroad tracks? Do you see that railroads being agreeable to this type of construction, prefabrication, acceleration, things of that nature?
Gee, that's a question I might have submitted, because the photo I showed on the first slide is a bridge over a railroad. That is a, I can go back to it. I go to home. There we go. That photo right there, that is a railroad crossing. The lower half of that pier is an actual crash wall. That is a railroad crash wall. It's a freight line that this bridge is built over, and that's all the more reason to consider prefabrication, because this particular pier was built in a day and a half to 2 days, so the amount of closures of the rail line to set these panels was very limited. So railroads are prime examples of bridges that you should be considering prefabrication and ABC on. And just because you have a railroad crossing doesn't necessarily mean you have to go to cast in place, that you can actually design these piers to handle railroad loading. And this particular pier was designed for that.
And I do know railroads like us to stay, get in and get out, because time is definitely money, and they're not disturbing their freight lines.
A railroad engineer one time told me, if we close a lane in a highway, it's an inconvenience. If we close a track, we shut the entire system down. And that's something to think about.
Okay, so with that, Mike, I'm going to go ahead and shut it down on the Q&A session. I want to thank you very much for that, and we're going to just give this back to Adirond. Adirond?
Right. Thank you, Ben. As usual, doing a great job on moderating the question and answer. And Mike, thanks for a great and very interesting presentation. Also, for everyone's information, we did send on the question box a link to some information on the linkage slab if you are interested. To get more information on design of the linkage slab, if you Google the design of the bridges for service life, the final report and the guide has some good information and good amount of design information for linkage slab. So on that note, we will conclude today's webinar and hope to have everyone back with us for the next month. Thank you.